so I'm going to record Module 7B, Lab 21, I think. Is it called 21 in your book?
Lab 7B is Lab 14.
7B is Lab 14?
Yeah.
Wow, I'm way off. Okay. What page is it?
62.
62. All right. Wow, that's interesting.
Honestly, a lot better than I thought it would be.
All right. So we're still talking about Newton's laws of motion. Who remembers the first law? We studied that last time.
Inertia.
Inertia. Also, we can say it what way? How do we say it? Objects
At rest or in motion do not
stay at rest or in motion unless acted upon by an unbalanced force, right? Therefore, things are going to they're going to continue doing whatever they're doing unless a force acts upon them. All right, so we're looking now at Newton's second law. It states when an object is acted upon by one or more unbalanced forces, the net force is equal to the mass of the object times, and that means multiplication, the resulting acceleration. So you'll have those blanks to fill in?
Yeah.
Okay, because the best way to express Newton's second law, is with a math equation. Okay, and that math equation is F equals ma. Force equals mass times acceleration. It's classic. It is not difficult. Easy math. Now, I would tell you that on this quiz I'll be sending home with you, you can use your notes to take this quiz, all right? So I expect you to make 100 on it. Also, you may need a calculator, and you may need a calculator for the midterm, which is next week. Okay, so when you come next week, bring your lab books. I need those, and if you're taking the test at home, make sure they're all recorded in the back, so then I can put that into Jupyter. And also, I can get you a lab grade, because right now your grade is based solely on your quizzes, and this doesn't really reflect your grade. Okay, so it'll really bring it up when I put the lab book in there, presuming your lab write-ups have been good. Yes?
Wait, when you say notes, do you mean like this book?
Yes, that book. I need that book. Right. You can use that book as notes to take your quiz. So take good notes, right? All right, so Newton's second law then is best expressed by a math equation, F equals ma. Total force, notice it's saying total force is mass times acceleration. Okay, well, that's going to be important in a little bit when we talk about adding forces together. Okay, so total force right here. So when an object is acted on by one or more outside forces, okay, we have that already. A force is a push or a pull exerted on an object in an effort to change the object's velocity. All right, this is a vector quantity, which means, of course, we need to put direction in there. And it's measured in the magnitude called newtons. So newtons is the unit of measurement for this, for force. All right, and we've named it obviously after Isaac Newton. So a newton is 1 kilogram meter over second square. Instead of writing 1 kilogram meter over second square, we just put an n. And n means that, okay? So the standard unit of force is the newton. All right, so force, push or pull. We have guys here pulling on the rope, right? One of them maybe end up stronger than the other, and here is the equation. So newtons equals mass, that's in kilograms or grams, right? Times acceleration, which will be meters per second squared, possibly something that we had calculated previously, okay? All right, let's watch a little video on Newton and his second law.
Sir Isaac Newton. He came up with 3 laws of motion. We've talked about some of these before in previous episodes, and we're going to talk about his second law of motion. Now, his second law of motion states that the strength of a force is equal to the amount of mass involved multiplied by any acceleration applied to it. That sounds a little complicated, but I have a simple demonstration to show you how this works. I have 2 objects. One is red and one is yellow, and that's neither here nor there, but this one is heavier, and you're going to have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have 2 different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now, what I'm going to do is I'm going to try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm going to put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough to, that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and... Could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of. If that price of fuel keeps increasing, we want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. McMillan Space Center, I'm Cam Cronin. Thanks again, Parnelli.
Okay, and furthermore, the one with more weight would have had the acceleration would have had to been changed. So if we had the higher mass with the same acceleration, it would have had more force. All right, but he was talking about not changing the force. All right, so let's do an example. Here we go. A man's car with a mass of 1,500 kilograms has broken down. He's pushing it to the gas station. Ignoring friction, with what total force must the man push in order to make the car accelerate 0.03 meters per second squared to the east? All right, we know we're working with a vector quantity here because we have a direction. We know we're working with F equals ma because it asked about total force, okay? All right, what about units? Of course, we're going to be using 1 kilogram meters per second squared, also known as the Newton. So here's the same question right here with a 1,500 kilogram car being pushed. We're ignoring friction. All right, let's go through the math problem.
This is our first problem with Newton's second law. We're given the mass of a car, 1,500 kilograms, and we're told that the man must push the car with an acceleration of 0.03 meters per second squared to the east. And the question is, what's the force the man must use? How are we going to do that? Well, this is a pretty straightforward application of Newton's second law. According to the law, force equals mass times acceleration. We were given the mass, 1,500 kilograms, so we could put that into the equation. We've also been given the acceleration, 0.03 meters per second squared east. So we'll put that into the equation as well. All right, so now we have our equation. Force equals 1,500 kilograms times 0.03 meters per second squared. Now remember, we can do the numbers and the units separately. So let's start with the numbers. 1,500 times 0.03 is 45. And the units, kilograms times meter per second squared is kilogram meter per second squared. Now you should recognize that unit. Kilogram meter over second squared is the same thing as a Newton. So the force is 45 newtons. But that's not the whole story, is it? Force is a vector, so we have to include direction. The man wants the car to accelerate east, so the force must be east as well. So our final answer is 45 newtons to the east. Now this was a fairly simple problem. Don't get overconfident. They get a little tougher from here.
Don't get overconfident. All right, the previous problem ignored friction, so it's essentially meaningless. Because friction is a real thing, right? It's a real force that is slowing motion down. So therefore, that's when we come to the idea of total force bringing friction in. All right, so friction subtracts from the force being applied because it's in the opposite direction. So if I'm pushing the chair this direction, friction is pushing against the chair in the opposite direction, okay? All right, so total force is equal to force M minus 4 friction. So 4 the force of the mass times minus force, frictional force. All right, so hey there. All right, so we're going to be looking for our total force. In order to clear an area, a construction worker pushes a large rock with a mass of 300 kilograms. Once he gets the rock moving, it begins to accelerate at 0.12 meters per second squared to the north. If the man is able to apply 400 newtons of force, so we have a force, what is the frictional force between the rock and the ground? So you see how we're approaching this? We're approaching this by knowing some of the information on the other side of the equation and have to do a little algebra here. All right, so this is the same problem written down here to the left, and let's watch how the steps we go through to get here.
In this example, a construction worker is pushing a rock whose mass is 300 kilograms. We know that the worker is exerting a force of 400 newtons. It's directed to the north because he wants the rock to accelerate to the north. We also know there's a frictional force. That frictional force opposes motion, so even though we don't know the size of the frictional force, we know it's oriented to the south. There's one more thing we know. We know that the rock is accelerating with an acceleration of 0.12 meters per second squared north. Okay, those are all the things we know. What we need to do is try and figure out what's the value of that frictional force. Well, first we have to think about what we've just learned. Forces add and subtract. So I've got two forces working on this rock, the worker's force and the frictional force. They're opposing one another. So the total force that's acting on this rock is the worker's force minus the frictional force. Now we know the value of the worker's force. That's 400 newtons. So we could stick that into this equation and get that the total force is 400 newtons minus the frictional force. Now remember, we want to figure out what the frictional force is. So we've got to figure out some way to get a value for the total force. Well, it turns out I can get that from Newton's second law.
Total force.
Remember, Newton's second law always deals with the total force exerted on an object. The total force is equal to mass times acceleration. That's Newton's second law. Well, it turns out we know everything we need to calculate the total force this way. After all, we know the mass, that's 300 kilograms. We also know the acceleration, 0.12 meters per second squared north. So in the end, we can evaluate the total force as 300 times 0.12, that's 36, and then the unit is kilogram meter over second squared, which of course is a newton. So we know that the total force is 36 newtons. Well, think about what we have here. We know the total force is 36 newtons, but up above, we have an equation that says total force equals 400 newtons minus the frictional force. So if we take this 36 newtons, we know that's the total force, and we put it into that equation, we find out that 36 newtons is 400 newtons minus the frictional force. So in the end, what does the frictional force have to be to make this equation work? Well, if the frictional force was 364 newtons, then 400 minus 364 would be 36. So that tells us that the frictional force is 364 newtons. What's the direction of the frictional force? Well, it opposes the motion, right? The motion is towards the north, friction opposes the motion, so the frictional force is 364 newtons to the south. It's important to understand what we did here. We have this equation, Newton's second law, which deals with the total force exerted on an object. Now, when there's only one force exerted on the object, the total force is equal to that force, no problem. However, in this example, there are two forces exerted on the object, the worker's force and the frictional force. Newton's second law only tells us about the total force. Well, the total force is the worker's force minus the frictional force. So when we use mass times acceleration, that's only giving us the total, which is the worker's force minus the frictional force. Since we can figure out the total force, and since we were given the worker's force, then we can figure out the frictional force, but we have to think about it. That's what makes these problems difficult.
Did you find it difficult? We just have to remember the steps we're going to go through, okay? Because the math is not difficult, is it? It's just the steps of getting there. That's the only thing. It's gonna have to, you have to remember that. Okay, so did y'all write all that down on your book in a box or something, and we're all good? We're good? Okay, great. All right, so we have kinetic friction and we have static friction. We mentioned this last time. Kinetic friction is that opposes motion that is already going. It's moving already. And then static friction is that opposes the initiation of motion. So I got to get it started first, and once I get it started, and it'll keep going because the laws of motion state that, right? Okay, I think this is just reviewing something from last week, if there's nothing to write down. All right, so here we're going to see a man needs to push a desk, which is 100 kilograms in mass, across the floor. The static frictional force can resist motion with as much as 196 newtons of force, while the kinetic friction force is only 110. That makes sense because it's already moving, right? So it takes more to get it moving than to keep it moving. We know that. How much force is necessary to get it moving? If the desk accelerates at 1.0 meters per second squared to the west, when the force is applied, how much force did the man use? All right, so we're just going to plug all this in and try to figure out the difference then between our kinetic and static. Okay, so we're going to go through again. All the stuff on the left is what I just read to you. Let's see.
This example actually has two problems in it, so we'll treat them independently. The first problem asks, let's suppose a man is trying to move a desk with a mass of 100 kilograms. And let's suppose the static frictional force between the desk and the floor is 196 newtons. How much force must the man apply in order to get the desk moving? So the first thing we have to worry about is what's the total force acting on the desk? Well, the worker is pushing on the desk, so that's a force, but friction is also resisting the motion, so that's a force. There are two forces, and they oppose each other. So the total force is the worker's force minus the static frictional force. Now we know what the static frictional force is. It's 196 newtons. So let's go ahead and put that in the equation. Now in order to get this desk to move, the total force acting on the desk must be greater than 0. Therefore, the worker's force must be just a little greater than 196 newtons. That way, when you subtract 196 newtons from it, you still get a positive answer, which means there is some force acting on the desk. So the worker's force must be just greater than 196 newtons. But that's not quite the end of the story, because force is a vector. We want the desk to move west. So the force the worker applies must be just a little greater than 196 newtons west.
That's a weird answer.
Okay, that wasn't so bad. The next part's a little trickier. The next part says, let's suppose that desk is moving. Well, if the desk is moving, then we know we need to use the kinetic frictional force, and that's given as 110 newtons. Also, we're told that the box is accelerating with an acceleration of 1 meters per second squared. And the question is, what force must the man apply to keep this acceleration going? Well, once again, we have to consider the total force acting on the desk. The kinetic friction opposes the worker, so the total force is the worker's force minus kinetic friction. Now we're told what kinetic friction is. It's 110 newtons, so we might as well put that in there. So the total force is the worker's force minus 110 newtons. But we know another way of calculating total force. We also know that total force is mass times acceleration. Well, we were given the mass, 100 kilograms, and we were given the acceleration, 1.0 meters per second squared. So we could put those into the problem as well. So we know that the total force is 100 kilograms times 1.0 meters per second squared. That works out to 100 kilogram meter per second squared. That's the same thing as 100 newtons. So what do we have here? We know that the total force is 100 newtons. We can put that into our equation above. So we now know that the total force, 100 newtons, is equal to the worker's force minus 110 newtons. So in the end, we have an equation here that says 100 must equal whatever the worker's force is minus 110. Well, if you think about it, the worker's force has to be 210 for that to work. So the worker's force is 210 newtons. That's not quite the end of the story, though, because the worker wants his desk to go west, so we have to include that direction. So the worker's force is 210 newtons to the west.
Okay, wow. That made me zone out just a little bit. I don't know about y'all. But the idea here also, I would write the word west instead of W. It looks like northwest, right? NW. That N is newtons. So don't get that mixed up with north. So maybe write out the directions so that you can tell the difference. Okay, so that just, I thought the first part of the problem, I don't like that it didn't have an exact answer. It has to be a little more than that. Okay, well, no duh, you know, so. All right, are weight and mass the same? The answer is no. Is that a question in your book? Are y'all done with your notes? Are we done with our notes? Is there a question? It's midway down the second page, it looks like. Are we good? What's above that? Something for our lab?
It says like on your own.
Some on your own. Okay, so go ahead and fill those in when you're doing your notes at home. Remember, next week, y'all, we do have our midterm. I want you to bring those books with you, and I'll be looking to see if those are filled in. Okay? Yeah, next week is the last day before Christmas break.
Wait, like filled in for like the labs, like every single section filled in.
Yeah, there's some things that wouldn't have been filled in, right, because we didn't do them or whatever. But yeah, go back and look at your labs and make sure you have a conclusion written for each one, what you learned from it, okay? That's what I really look for, the conclusions, okay? Weight and mass are related, but they are not the same. That was there was a blank you're filling in? They are not the same. Okay. So, what is weight? Weight is mass times acceleration due to gravity. It depends on where you are. We're on the planet Earth, so we know what gravity is, right? Isn't it 9.8 meters per second squared? Is it 9.6? All right, so because we're on the Earth, we're not going to be changing that. If we were to go to the moon, it would change. But your weight would change, your mass would not, okay? Mass is basically how much stuff is in you, right? And that stuff's going to stay the same on the moon. It's just not going to weigh the same. Because of the gravitational pull of the moon is different, okay? So in this particular case, that acceleration is due to gravity. So we know that number. All right. Example 7.3. This is probably one of those boxes you're writing in, yeah? An astronaut has a mass of 121 kilograms. What is his weight on Earth? Okay, so we're going to take that number, mass. We're going to put it into mass times acceleration. What are we going to use for acceleration? The gravity constant, okay? So 9.8 meters per second squared. So all we have to do is figure out the mass, right? So we know the mass, we know the acceleration, so we're going to find out what that is. Write the equation 7.3 and rearrange so the unknown will be on the left side. So that's going to be our force, m times g, that's gravity, that's acceleration. And so we're just plugging those numbers in, mass, acceleration due to gravity, and we're going to see he weighs 1,185.8 newtons. That's newtons, not pounds. That would be a big guy. So notice we're still using that equation right here. It's just remembering acceleration is gravitational pull.
What do I do if I wasn't there for the lab?
Just write absent on there. All right, what is the astronaut's weight on the moon where the acceleration, look, the A is going to change to 1.625 meters per second squared. So nothing else will change. His mass will stay the same, right? But his acceleration will change because he's on a different place. So we have our mass, 121, that stays the same. Doesn't change just because he's on the moon. But this changes, the G, which is taking the place of A right there. We're going to look at this in newtons. Write the equation set point 3 and rearrange the unknown on the left side, which we know, we're just replacing that number here with a much smaller number, and we're going to see he's only 196.6 newtons on the moon. So quite a bit less, right? That's because the moon is so much smaller than the Earth that its gravitational pull is that much less on there, okay? But notice his mass did not change. So, notice how in both locations the astronaut's mass is the same, but his weight is on the moon is only about 1/6 as his weight on the Earth. So that's, if I ask you what's Newton's second law, you can just write down F equals ma, and that would be the proper answer. F equals ma, force equals mass times acceleration. And that's the whole idea. Would you rather be, have somebody shoot a bowling ball at you or a balloon, so the balloon's gonna be less force on you, right? It won't hurt you. Would you rather, I guess I could say kick a soccer ball or kick a bowling ball? Bowling ball's gonna hurt. Because it's got more mass. All right, which I think we're moving on to the third law now. Is that what your book says? Newton's third law. For every action, there is an equal and opposite reaction. Case classic?
Opposite is a blank.
Opposite what?
Is a blank in here.
Let's see if I have it. Reaction. Okay. We'll probably get to that if there's a blank. The equal and opposite reaction. This is I'm pushing against the wall is pushing back on me. Okay, the action and the reaction. Somebody just recently told me that there was some sort of experiment that did not conform to Newton's third law. And so they were trying to tell me that it had been disproven. I said, well, just because it doesn't conform doesn't mean we've disproven the whole law. It's a law, right? It's going to take a lot to disprove Newton. Can we? Sure. Yeah, he's not sacred. If something comes up that changes it, it'll do it. But it'll make big news. It'll be a huge story. So I haven't heard about it, so I don't know. Let's watch a little something to illustrate the third law.
Rockets and missiles make use of Newton's third law. Consider, for example, the rocket that launches the space shuttle into outer space. When it fires its engines, the resulting combustion pushes gases down and out the bottom of the rocket. Since a force is pushing down on those gases, by Newton's third law, those gases must push back up on the rocket. The force of the gases pushing up on the rocket is what gives the rocket its lift.
All right, so the force pushing down makes the rocket go up. Yeah? Okay. So here's a cannon, someone's going to light it. There's going to be a force exploding the cannonball out, but it causes the cannon itself to move backwards. Right? So the cannoneer, the guy manning the cannon has to be careful not to be right behind the cannon when he shoots it because it'll smack him. Just be careful. I always wondered why they put them on wheels. I guess they have to move them into position or whatever, but you'd think they wouldn't want to be able to. Here's a lady with a gun. She's clearly not very good at it. Yeah, she's not holding it right. She's a dummy. Okay, be careful. All right, this is one of my favorites. This guy is a professor in a college class, as far as I know, and he's going to illustrate the third law of motion.
What I've got here is a simple plastic bottle, but if you look on the outside, there's a couple of vents that are angled backwards. If you have a look closer, you can see the vents. I'm going to fill it with liquid nitrogen and boil it. So, liquid nitrogen. As I say, one of the neat things about being a physicist is you get to play with some really fun toys. And this is liquid nitrogen, which is one of the more fun ones. It's about a couple of 100 degrees below zero. Now, so what I've got is I've got a boiling liquid. Here I did this with steam.
Boiling on its own.
I'm going to do it with liquid nitrogen. And I'm going to warm up the liquid nitrogen by putting in, this is just ordinary water. And we get this wonderful little jet engine.
It's spinning. The bottle is spinning.
So what's happening? There's high pressure in here. The pressure forces, warm it up again. The pressure inside forces the gas out. And the Newton's third law reaction force pushes the cylinder in the opposite direction, causing it to spin. There's a force of this plastic bottle on the gas going out, and there's a Newton's law force of the gas on the bottle spinning it in the other direction. And I have a jet engine here. Now, this is not an ordinary fire extinguisher. Every single reduction valve has been removed from this thing, so it's a fairly lethal fire extinguisher. When I crack the valve, it will empty itself in about 10 seconds. And I'm going to sit on the skateboard, hold on to this thing, crack the valve, and hopefully I will hurtle along behind the building. There's a huge force of the cylinder on the gas. And then that gas pushes back on the cylinder and on me, accelerating me. So,
Okay, there was somebody there to catch him. I would have been, concerned about maybe hitting the wall, like getting crooked or just falling off of the thing like this, So I'm not going to do that. Yeah, I'm not going to do that. All right, so now that's Newton's laws. You need to definitely be sure that you know all three of his laws and know them well, okay? Remember the quiz you're taking home today you get to use your notes on. But when it comes to the midterm, make sure you know those three, okay? All right, now we're going to be learning about the fundamental forces. Do you have a whole page of notes you have to do? Yeah, pretty much? Okay. All right, so there's 4 fundamental forces that we know about and we'll be learning about. Here they are. The number one, I don't know if we're talking about in this order or not, but the electromagnetic force, or the EM force, also known as the electromagnetic or EM spectrum. It's quite vast, actually. Number 2, the strong nuclear force. Nuclear meaning the middle of a atom, in the nucleus of an atom. Number 3, the weak nuclear force, also in the nucleus. And number 4, gravity. So these are the 4 fundamental forces on this planet. Can you guess which one is the strongest?
Weak? Isn't it like weak?
Let's go for the obvious on this one. The strong nuclear force is the strongest. What is the weakest? Don't pick weak nuclear force, because it's the second strongest. What's the weakest?
Isn't it actually like gravity?
It's gravity.
Yeah.
Gravity's the weakest.
Right.
In fact, we don't even know if gravity's a force. In fact, the fact that it's mentioned as a force in your book right here would get some people mad about that, because they really, really will die on that hill that gravity is not a force. And I'll show you why that they say that here in just a minute. All right, but you may very well have the question, name the 4 fundamental forces. And you'll have to write these down. Of course, in your quiz, you'll be able to use your notes to do that. But in the midterm, you won't. So you need to know, okay? And in fact, studying old quizzes is a good way to get ready for the midterm, okay? Old corrected quizzes. I just found in my notebook here that I have not returned a quiz to some of my chemistry kids, and I'm like, oh no, because I want them to have that so they can study it. Okay, so here we go. We have electromagnetism, the weak force, the strong force, and gravity right there. So we're going to talk about each one of these. I'm not sure what order we're going to take them in, the 4 fundamental forces. Looks like we're going to start with electromagnetism. Acts between electrically charged particles. Okay, so notice here we say the weaker to the stronger. Oh, look at me. I put weak force above electromagnetism. I was wrong about that. Okay, I was pretty sure the electromagnetism was closer to gravity right there. All right, this table right here is just telling us some things right here. Gravity, all particles with mass experience that. The weak force, we have something called quarks and leptons inside of atoms, we think, possibly. Electromagnetism, it says here electrically charged particles. It's really not limited to that. We're going to see some weird theories out there that may involve, that actually may put all of these forces together on the EM spectrum. It's possible. It's possible. We're not exactly sure. And then the strong force, we're going to look at these weird things called quarks and gluons that are really theoretical. But all of science is, yeah? So, all right, so let's talk a little bit about the electromagnetic force. It exists between particles with electrical charge. Okay, so those are the blanks you're filling in on that one. Good, okay. There are 2 aspects to this force. We have attraction and repulsion. So what we're seeing here is that like charges repel. They move away from one another. You know this when you played with magnets before, yes? How you can make things move without touching them, yeah? By taking a magnet and moving them around, right? You could either touch it and drag it, or you could push it with the opposite force. So if you take a north-south pole of a magnet and turn it the other way, they'll stick, but if you turn it this way where north is north and south is south, they will repel one another. Okay, so that's a fundamental concept, all right? Opposite charges are attracted to one another. So if you have a balloon that's sticking to you, or a sock that's sticking to your pants out of the dryer or something like that, that's because I have the opposite charges and it's stuck there, and if you pull it away, you'll hear a little static electricity, pulling that away. All electromagnetic. So electricity and magnetism are absolutely tied together, and we'll learn more about that as we move on through the year next semester. The strongest force in all of creation is the strong force, and I'll show you why here in just a minute. The strong nuclear force is related to the attraction within atoms and is the strongest of the fundamental forces. So I want you to think for a second, what is in the middle of an atom? What is in the nucleus of an atom? What's in there, we think? Protons and neutrons, right? The electrons are not in there, right? Where are the electrons? Orbiting, right? They're orbiting around there. And so that means packed inside that little tiny high density nucleus, we have a bunch of positively charged particles. What do we know about positive next to positive? What do? They repel. So let's think of like a large atom. Let's talk about gold. It's pretty big. Here it is. Gold is number 79. So that tells us it has 79 protons in its nucleus, right? We don't really care about neutrons at this time. Neutrons give it mass, but they don't give it any other charge, right? So it's got 79 positively charged things in this little tiny... Why are they not just moving away from each other? You see what I'm saying? It seems it's like, we know they repel. Why aren't they repelling? Because of the strong force. Okay? So here we go. The protons are positive, like charges repel. So how is it that protons don't repel each other in the nucleus? The strong nuclear force is so strong that it overcomes the natural repulsion of like particles. Wow. So honestly, someday if God's ready to end it all, he could just say, take away the strong force, and everything will just explode. Whoosh, everything will just fall apart. So that's just the fact that we're walking around, we have stuff, we have matter. It's a miracle. It's a miracle of this thing called the strong force. So what exactly is the strong force? How? What's the mechanism? We do not know. We have ideas, we have theories and things like this, and we have these weird words like gluons and quarks. All right, so nucleons, both protons and neutrons together, attract one another by this strong nuclear force. We do believe that neutrons do have some role in keeping those, in that strong force staying stable. All right, so in other words, it wouldn't be the same without neutrons. So neutrons are necessary. A lot of times we'll say neutrons just give mass. I don't know. There's something here the neutrons are also active in, okay? Only protons repel one another. We know that because we know the neutrons are neutral. Oh, we have the weak force. Okay, I thought I had a picture of you showing it. When they show a gluon, it kind of looks like a little strip of tape going, well, in the picture, not in real life, right? We can't see, they're too small to see. But when it showed it that way, it showed that those positive things are being kind of grappled together with this thing called the gluon. And then the quark is the whole thing together. All right, so we're at the weak force. The weak force operates in a small range, like the strong force, in other words, inside of a nucleus, and it's related to something called radioactivity. So it turns out that some atoms, their nucleus is unstable naturally. It's naturally unstable. And what that means typically is that the protons and the neutrons together, the strong force in there, will lose a portion of it, okay? And that weak force will end up sending some of those things off, okay? So it's just saying that the neutron right here, we could have also theoretical. The idea of a proton and an electron, remember they're positive, negative, they're attracted to each other. So if we put those together, that big thing and that tiny thing, and added those together, we have a neutron. Okay, it's neutral. It has that much mass difference, that teeny tiny itty bitty mass difference, conferring mass to the atom. So that's one of the theories that are out there, okay? And so what will happen sometimes is that if the neutrons are too unstable, they'll shoot one of these out, a proton or two protons. This is what it looks like. When an atom is radioactive, it emits particles or energy in order to stabilize itself, okay? If it's unstable, it's trying to reach stability. And these particles are sometimes called quarks. Okay, so we have bosons and quarks, and then the weak force is taking those and sending those out in a radioactive way. It's literally shooting a particle out of an atom, and it's doing it naturally. Now, some of the atoms that we've synthesized in the laboratory, so in other words, they're synthetic, they're almost all of them, I believe, are radioactive. They're always going to fall apart. Okay, so they're falling apart. But we can use that for some things, sometimes for energy. Remember, if I can get something moving, I've got energy. And if I can get energy, I can light my room in my house, right? This is all trying to find energy sources is really amazing. All right, so here we go. We have our nucleus, and what'll happen is we'll shoot some things out when they become unstable. All right, and so it looks like here a little electron, a little proton. We will get more detail about the type of radioactivity. There's really two main ones where they'll send out an alpha particle or a beta particle. All right, we're looking at a beta particle right here. Okay, and when it shoots out like that, you could even think of it as shining a beam of light. There's energy associated with it because it's moving, and sometimes you can see it in light. Okay, here's the universal law of gravitation. The gravitational force, I use that word lightly, states that every object in the universe is attracted to every other object. It's called the universal law of gravitation. Another one of Newton's laws. Remember, it's not just that stuff is pulled down, but the same force or phenomenon that is pulling stuff down to the Earth is the same thing holding the moon in orbit around the Earth, and the Earth in orbit around the sun. That's the universal law of Newton's law. All right, but we're going to see right here, it shows a little bit of the bent space-time situation, which would make gravity more of a physical result of it resting in a certain position in space, like the bowling ball on the trampoline. Okay, that's why people get bent out of shape about this. I don't know, do I have a video here? What do I have? Oh, Schoolhouse Rock.
Help and wash the dishes, and I drop a cup of. Why does everything fall down instead of a tub? Riding up a hill I spill and hit the ground. Wish I could fall up instead of always falling down. Down, 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 down. I'm a victim of gravity. Everything keeps falling down on me. No matter where I go, the force is there, I know. Down, 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 down. It's all around town now. It's like a magnet deep inside the ground. When I lift something up, I can feel it pulling down. Pulls me in the pool. It pulls rain down on me. I'm a victim of down, 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 down. Gravity, yeah. Galileo. He did experiments with a force he couldn't see. He allowed that all things fall to Earth at the very same speed. Galileo didn't know it yet, but that was due to gravity. The moon goes round the Earth and shines its silver light. The Earth goes round the sun, makes the seasons right. It isn't love that makes the world go round, you see. Power of gravity. But please don't tell Mary Jean. Down, 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 down. Without Earth's gravity to keep us in our place, we'd have no weight at all. We'd be in outer space. The sea would float away, and so would fields and towns. Down, 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 down. Isaac Newton underneath the apple tree. One hit him on the head, he said that must be gravity.
Newton's law of gravity says that every object in the universe pulls on every other object. The bigger the object, the stronger the pull. But the greater the distance between the objects, the weaker the pull becomes. Come back, Mary Jean.
Don't call me clumsy, don't call me a fool. When things fall down on me, I'm following the rule. The rule that says that what goes up comes down like me. I'm a victim of down, 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 gravity. Shooby-doo, down, down, down.
All right, I'm a victim of gravity. I feel it. explain it. You know, scientists don't just want to make observations and say, oh yeah, that's what happens. They want to know mechanism. They want to know how, okay? So there are a couple of theories out there about gravity, and one of them is called the graviton theory. So what causes gravity? We don't know. But this idea of gravitons is kind of interesting. It literally says there are these little particles that are exchanged between things. And since the Earth is bigger, way bigger than me, the particles that we're exchanging are far weighted to the Earth's particles over mine. That's why the Earth is pulling me down. Okay, that's the idea of these gravitons. And then the closer we are, I'm touching the Earth, right? So there's got that max pull. But like the farther I get away, in the video it barely said, it says the farther away the less the pull, right? The girl's running away, right? The farther away the less pull. So the idea here, and we can do this as part of our lab, is that if I'm throwing a ball to you and we're standing like this and we throw a ball back and forth, but then we start to move away, what are our chances of catching the balls now? A little less and less and less and less the farther we get away. So that's the graviton theory. All right, so this comes in like this. Here's our two things. Look at the little deals coming in between there, showing that they're being exchanged between those two. The theory predicts that objects with mass quickly exchange particles called gravitons. The closer the objects, the easier it is, like throwing the little balls, right? And therefore have easier access. That's gravity. Gravitons are purely theoretical, but there are particle exchange and other instances are well known. So the idea that there are little particles. You know, for instance, when we do the study of light, there's studies of light that suggest that light travels as a wave, and there's equally valid studies of light that suggest that light travels as a particle. We don't know, so we call it the particle wave theory. It's a dual theory. All right, so once again, this is just the mystery deal. Another proposed by Einstein is based on his general theory of relativity. This is the idea that it's not really a force. All right, although there is a push and a pull, and that's the definition of force, a push or a pull. Einstein suggested that space is bent, therefore causing objects to move naturally in a circular path. This is the bowling ball on the trampoline theory. So you can see right here, if it's bent, then something moving around it, if I start to move it, it's going to move naturally in a circle around that. Eventually, however, what's going to happen? It's going to eventually be pulled into it, isn't it? So the idea here is if the Earth is spinning around the sun because of bent space-time, then eventually it should end up in the sun. I don't know, you know, what we're talking about timing-wise. I don't know that we have any evidence that the Earth is any closer to the sun than it's ever been. But it is being kept in orbit by this. This is Einstein's theory. Let's watch a little video about it. See if it helps us explain it.
In order to understand gravity, we need to start with a simple classical mechanical explanation. In classical mechanics, we have two famous theories. The first one is the Newtonian version of gravity proposed by Sir Isaac Newton, which simply states that gravity is caused when two objects exert gravitational attraction on each other. Then came Einsteinian gravity, which is the currently preferred view of gravity, which shook things up a little bit, claiming that space and time were interwoven into a single entity called space-time, and that the presence of an object distorted space-time, and that it was this distortion that we perceive as gravity. However, the problem with the classical mechanical explanation of gravity is that when we try to understand gravity on a quantum mechanical level, our classical mechanical view breaks down and fails to comprehend what gravity is on a microscopic scale. Then in the 1930s, two Russian physicists proposed a theory that would garner a lot of interest. This shocking theory stated that just like how the electromagnetic force is transmitted through the exchange of subatomic particles called photons, the force of gravity was transmitted by a hypothetical subatomic particle called a graviton. The graviton can be explained by another theory, string theory. To sum it up, string theory is a controversial theory, stating that all the matter in the universe is made up of tiny, vibrating, one-dimensional particles called strings. Strings can fall into two classifications, open and closed. Open strings, aka the matter you and I are supposedly made of, are permanently attached to our universe, which the theory suggests is a giant entity called a brain. Closed strings, on the other hand, aren't attached to our universe and are free to travel to other universes if they exist. Gravitons are supposedly theorized to be closed strings, which means they can leave our universe or brane since they aren't attached to it and travel to other universes or branes if they exist. In other words, one way to detect gravitons is to check for gravitons coming from other universes, but this is a highly unviable option since other universes probably don't exist, and even if they did, they are billions or possibly trillions of light years from Earth. This whole distance thing poses an issue because contrary to popular belief, the speed of gravity is not instantaneous, but rather gravitons are calculated to travel at the speed of light. And while the speed of light is undoubtedly fast, it is still no match for the vast distances found in the cosmos. Going back to what I said, general relativity is good when it comes to explaining the realm of our everyday life, but on a quantum mechanical scale, it is utterly useless. So the ultimate question to be answered is, do gravitons succeed where Einstein failed? Well, the answer to that question is not at the moment. While gravitons offer a nice explanation of gravity, we are yet to discover their existence. So what exactly is it about gravitons that makes it so hard to discover? You see, gravity, contrary to what many people believe, is one of the weakest forces to exist. In fact, the bonds holding together a hydrogen atom are stronger. Another example to prove my point is how easily I can pick up an apple, despite the entire Earth exerting a gravitational pull on it. From a quantum mechanical view, the reason for gravity's lack of strength is due to the fact that gravitons interact very weakly, so as a result, detecting a graviton would be very difficult. Referring back to classical mechanics for the final time, while the theory of gravitons may not do what general relativity couldn't, general relativity did give scientists a nice starting point. According to general relativity's explanation of the distribution of the mass and energy in the universe, if there is a graviton, it's a massless particle with a spin of 2. Scientists from Fermilab to CERN are looking for this particle with eager eyes in the physics community, but until we find and confirm the existence of gravitons, they just remain a theoretical explanation of our universe. If you enjoyed this video, be sure to leave a like.
Okay, like I said, theory, right? So, but he mentioned several times it was controversial, that string theory and all that. You know, if there are other universes, oh my goodness, that gets into a lot of philosophy, which, you know, gives me a headache. So the idea of gravitons, if it's a massless particle, how in the world are they going to find it? I don't know how they're going to find it. So once again, it's a little bit of a mystery, and you will meet people that don't think that gravity is a force at all, but just a result of a physical situation, of being in a time-space warp. Yeah. All right, so we're going to do lab now, and we're going to work with a couple things inside, then we're going to go outside to do a part of our lab, okay? So I'm going to turn this on.